In the last episode, we explored how massive stars spend millions of years fusing progressively heavier elements deep within their cores. Layer by layer, the star builds new elements through nuclear fusion, hydrogen into helium, helium into carbon, carbon into oxygen, and onward through progressively heavier stages of fusion. For millions of years, the enormous outward pressure generated by these fusion reactions balances the inward pull of gravity, but eventually the process reaches a dead end. When the core of a massive star becomes dominated by iron, fusion can no longer generate enough energy to support the star against its own weight. The equilibrium that sustained the star for millions of years suddenly begins to fail. The star spent millions of years building the iron core. The collapse itself unfolds almost instantaneously. Gravity, which had been held at bay for most of the star's existence, now overwhelms the core completely. And what happens next will produce some of the most violent and extraordinary objects in the universe. Come walk with me. As astronomers studied the lives of stars, they came to understand that stars do not all share the same fate. The end state of a star depends largely on the mass it had when it formed. Lower mass stars, like our Sun, eventually become white dwarfs. Stars born with roughly 8 to 25 times the mass of our Sun may end their lives as neutron stars, and stars born with even greater masses may continue down a path that leads to black holes. If you've been with me since season 1, you'll remember that type 1a supernovae played a central role in our discussion of the accelerating expansion of the universe. So we'll return to that story shortly. In other words, the story of a star's death is largely determined at the moment of its birth. The initial conditions matter. The mass of a star at birth largely determines what it will become at death: a white dwarf, a neutron star, or a black hole. In this episode, we'll explore those 3 possible destinations and the boundaries that separate them. Lower mass stars, like our Sun, do not explode as core collapse supernovae. Instead, they eventually shed their outer layers into space. What remains is the hot, dense core of the star. That remnant is called a white dwarf. A white dwarf is already an extreme object. It can contain a mass comparable to the Sun, compressed into a volume roughly the size of the Earth. But a neutron star is smaller still. In this comparison, the white dwarf is on the left, the neutron star is in the center, and the Earth is on the right. The important point is not just size, it is density. As we move from white dwarfs to neutron stars, we are moving into a much more extreme state of matter. You may recognize this graphic from season 1. At the time, we were interested in type 1a supernovae because they helped astronomers measure vast distances across the universe. Those measurements ultimately contributed to the discovery that the expansion of the universe is accelerating. Today, we're looking at the same phenomenon from a different perspective. Astronomers eventually discovered that white dwarfs cannot have unlimited mass. There is a critical threshold at about 1.4 times the mass of our Sun. If a white dwarf approaches that limit, it becomes unstable. Under the right circumstances, a white dwarf can acquire additional mass from a companion star. When that critical threshold is crossed, the result can be one of the most powerful explosions in the universe, a type 1a supernova. At this point, you may be wondering something. I just told you that stars like our Sun eventually become white dwarfs. Yet I also said that a white dwarf becomes unstable if it approaches 1.4 times the mass of our Sun. How can that be? The answer is that the mass of a star when it forms is not necessarily the same as the mass of the remnant it leaves behind. During its lifetime, a star can lose a substantial amount of material. Our sun, for example, is expected to leave behind a white dwarf containing only a fraction of its original mass. Some stars begin life with much greater masses than our sun. Stars born with roughly 8 to 25 times the mass of the sun may end their lives as neutron stars. When these stars exhaust their nuclear fuel, the result can be a catastrophic collapse of the stellar core. The collapse triggers a powerful supernova explosion. In some cases, the event also produces enormous jets of energy that can be detected across vast distances. What remains behind is one of the most extraordinary objects in the universe, a neutron star. But not every massive star stops at the neutron star stage. Stars born with even greater masses may continue down a path that leads to black holes. For decades, black holes existed only as mathematical predictions. Then, in 2019, astronomers revealed the first image showing the environment surrounding a black hole. The black hole itself remains invisible. What we are seeing here is the glowing material around it and the shadow it casts against that background. Black holes are among the most fascinating and mysterious objects in the universe, and for the rest of this season, they will be our destination. So come walk with me.